Okay, now there is something that we should be aware of. Now that we've learned diastereomers and enantiomers, there's actually a trick that Fisher projections are pretty good at catching or helping you catch. What happens if with this molecule, let's say, so here in this particular case, I have made the top and different from the bottom, but you can easily have a compound that, can I go up here? Well, that's awfully coded in letters, but let's just steal this one again. I can copy, and let's just go back down here and paste. Okay, and let's see if I can surgically remove some of the... Well, that's good enough for me. Let's say you didn't have the alcohol on there. Okay, now this is an interesting example purely from the perspective of this being not a chiral compound at all. And what's crazy is you just saw me delete the OH, right? And I know it's not a chiral compound at all because I can draw a mirror plane through here, okay? And everything on this side of the mirror is going to be, well, not the same because that's not a mirror plane, lol. That's why Fisher projections are so cool. Actually, the mirror plane is the opposite of that. It is the one where the BRs are back. This is their mirror plane, right? And you don't notice it's a mirror plane, I guess, because it's the way it's drawn. That's not really looking like a mirror. But it will look like a mirror much more when I draw the Fisher projection, okay? And that's how we know, and that's why Fisher projections are so useful. Because if it's got a mirror plane through it, it's not chiral. Them's the rules. And so let's draw little bow ties here. And remember we got to rotate about here. Let's get rid of that stupid because that's not intuitively helpful. But if we rotate around this, and our actual compound now, which would make sense, is going to be full on that. And that BR doesn't really change. And you will actually be able to see now the mirror when we bring it forward, because now that, which is supposed to be a BR now, whatever that is. And obviously, it's a lowercase r because we're using the periodic table last I checked. As we rotate that around, so now the bromine is actually going from behind to the front, and that's an H. Now you probably can very clearly see that there is a mirror plane once I've rotated this around. And in this particular case, now that I've rotated it around, what you end up with is it doesn't actually make any difference, right? That's what's so intriguing about these types of compounds is, which side do I draw the bromines on? Because if I put my little eyeball of science on that side, or this side, you're supposed to look at it from this side, right? So you look down, and you don't really have like a good idea which one's the top. I mean, arbitrarily, I guess I could say if that's the top, then the BRs are on that side and that side. But there's no real reference here. There's no real reference for me to actually assure you that I am saying that this corresponds to this, because this it could also correspond. There's just no way for you to verify. Like, I cannot assure you with 100% assuredness that this corresponds to this, because they're symmetrical, right? So this whole getup, right, unfortunately can refer to both the R and the S configuration as well as the S and the R configuration, all right? Because there's just really no good way. I mean, we can assign R and S individually, all right, CH2, CH3. We can still draw an enantiomer here. All right, we can still do that. We can still number them and say, that's 1, 2, 3, circly around, circly around. So that is then going in a clockwise direction, so that must be the S configuration. And number them over here. So that's 1, 2, 3, right? Because this carbon is attached to a carbon, that carbon's attached to a bromine, so that has to be 1, 1, 2, 3, circly, 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 circly. And that's the opposite direction, and so we flip that around. That's the S and the R configuration. And we can confirm it up here because I have essentially just taken the S and the R configuration of these two. So S and R where the bromines are pointing that way, S and R the bromines are pointing that way. But again, all I have to do in order to make these two compounds identical is go doop 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 doop, and then flippity 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 flip. And yeah, now they're the same compound, although one is upside down and the other's not. But they are the same compound. Imagine all the letters flipped around at the same time. And if those two are the same compounds, then they are not actually mirror images. They're just the same thing. And that gives rise to a new term where you have what appear to be enantiomers, but they're nothing but enantiomers of lies. And they're called meso compounds. Meso compounds, also enantiomers of lies. Well, whatever makes you feel happy. But meso compounds aren't chiral, because I totally just showed you why, hopefully. There are other things that can sort of trip you up to make you think something is a chiral compound when it's meso, and chairs are pretty notorious for this, so let's work on one of those. You can draw a configuration where you have a CH3 here in the equatorial position and a CH3 here in the axial position. Let me resume this. And draw a mirror here, and you can show the CH3 comes out here. Okay. And then that is CH3 here. Now, if you weren't savvy enough, you'd probably see these are non-superimposable images, right? That you can take this, bring it over here, flippity floppity flip flip flam, all you want, and you won't be able to superimpose it. But you know that they're related by a ring flip, because we've done this before. In a prior lecture, we show that you have an equilibrium actually that exists over here, that this goes through some sort of boat thing initially, right, where you have a boat, after it comes through a twist boat, and that means that in this configuration you have a CH3 that's going to pop out this way and a CH3 that's going to go this way. Okay, and then it's going to end up into a configuration that brings it over here. All right, so watch out for, and we remember what this is called, a conformational isomer. All right, all that is just two different conformations of the same molecule. And you can do the same thing with a bond that you can rotate around. So chairs are pretty good at it, because chairs actually, you know, this flipping is very fast on this molecule. They can be slow flipping too. And that can make you think that you've got a chiral compound when in fact you don't. Same thing goes for ethane-like derivatives, where you have something that you are tempted to say, ooh, this looks pretty chiral to me, right? Because I can draw a mirror here, and now I have got a configuration that looks like this. Just because you can draw a mirror plane, again, it has nothing to do with the fact that this is a chiral compound. Just having a mirror image doesn't make it chiral. Your left foot has a mirror image with his right foot. Those are two different feet. But a ball has a mirror image. Everything can have a mirror image. It doesn't mean that you can't just take this thing in the back and rotate it around, and then you end up with that. Easy, right? Exact same compound. Now, I had mentioned that you cannot separate enantiomers based on physical properties, but you can separate diastereomers based on physical properties. And I kind of wanted to cover that a little bit more into detail. And so let me draw this pair of diastereomers here to sort of illustrate the idea that you can have different physical properties in diastereomers. For instance, this one has a melting point of 158, right? And so I've drawn not a mirror plane, that was quite silly. I'll draw the diastereomer on this side, and there we go, not mirror planes, clearly the diastereomer. And you can see that, as I discussed in the last lecture, right, that one of these molecules has a dipole no matter what you do, and you can look at the last lecture. That one gives you a higher melting point than the other one, which you really can't create a dipole in that system. So you got a nice dipole here, and in the other system, and no matter what you do, there's just no dipole that occurs in that. So higher dipole, higher melting point. Makes a lot of sense. Now, how do you translate this into a way to separate enantiomers? Okay, and that is done by creating diastereomer starting with a chiral compound. So for instance, if you had a chiral alcohol, you could create a diastereomeric ester. And to understand what I mean by that, we have to, well, let's take a step back. What do I mean by an ester or making an ester? Well, you make an ester. So an ester is made from a carboxylic acid and an alcohol, all right? You take these two things together, you mix them together, and there's actually an equilibrium that combines these two into an ester. This is called an esterification, right? And you can see how I am going to take these two carbons, and let's make that red, and attach it to this carboxylic acid. And we'll get into the chemistry later on and how esterifications work. But the point is that you can combine a carboxylic acid, one molecule, with an alcohol, another molecule. All right, so if you have chirality associated with both of these molecules. So for instance, if we started out with a chiral acid, right? So actually this is a racemic. So that bromine is in a mixture of R and S. And I wanted to separate the R and the S, a configuration of that carboxylic acid. I would make a diastereomer. And in order to make a diastereomer, we would have to start out with an enantiopure alcohol. And so that is a known. 100% of that is going to come in as exactly that enantiomer, all right? Now, we're not trying to resolve this compound. We bought this from Sigma Aldrich. We're going to add it. The one we're actually trying to figure out, we're separating, is this one over here. And that one is a mixture of R and S configurations. All right, and then I use my little chemistry reaction here, my esterification, and what I end up with is a BRH. I have yet to make this make any sense at all, but I do have a 100% in stereopure center over here, okay? Now, what this means is if I draw my two possibilities, all right, my two possibilities on this side are essentially, I have a compound that looks like this, where I have and I got my Br compound, that's coming out here, and then that's my H over here. And then this is always going to be the same because I'm smart and I bought an enantiomerically pure alcohol, so that's one possibility. And then the other possibility is I've reacted it with the other conformation where the H is coming out and then the Br is going in the back. All right, and this is back here, and I got my H. This is the same. That started out pure, stayed pure. All right. Now these two are related by their diastereomers, okay? it creates a diastereomeric ester, because what I started out with is something that is always conformationally pure, and we can actually now label them. We can do this as an exercise, where this chiral center, that's going to be a 1, that's ethyl, it's going to be 2, and that's going to be 3. All right, and I've conveniently put this hydrogen in the back already, so that allows me to ensure that I always have this same sort of configuration in both of my compounds. So I'm always going to have on this side an R. All right, and then this one, actually, I have called this a bromine, not an R. And that's going to be 2 because that's a carbon that goes to a bunch of oxygens, so that's going to be 3. And now this one goes this way. Hydrogen's conveniently located in the back. And this one is going to put me there, put that there, put that there. And I just realized that I've donked up, didn't I? Yes. Hydrogen is now in the front, and the bromine is now in the back, which is pretty embarrassing. Alright, whatevs. It's now here. And I also know that since this one is going to be coming around in a clockwise and a counterclockwise direction, that's going to be S. And then this one has to be R. Although you can kind of see that this is going to go this way, and this way. The hydrogen is facing towards you in this particular configuration, which means that you got to mentally flip it around. And when you mentally flip it around through this axis, you will note that it now rotates in the opposite direction. So we're safe. What we end up with is a conformation that is S, R, and one that is R, R. All right? And those two diastereomers can be separated because they have a difference in boiling point, melting point, polarity. There's something different about them. Probably it's maybe not a lot, but there's some degree of difference, and that allows us to be able to distinguish in how we can use chirality, or we can use that diastereomeric difference to produce a new compound. Now, the value of chirality is pretty significant. So chirality, because we are humans and we are chiral, that means that we interact with chiral molecules in a very specific way. We are made out of chiral proteins. Our proteins have amino acids, and those amino acids have specific chirality. They fold into specific shapes. And so our body recognizes chiral centers differently and responds to them differently. Okay, so if we were to take a common chiral molecule that looks like this, and it's common because it's a I believe it's a terpene, the naturally derived compound. They're from the family, the limonene family, and this compound smells like lemons. All right, it has a chiral. There's an enantiomer, I should say. That is the opposite. All right, and that one smells like oranges. All right, and there's the only difference is in this center right here, and you end up with a compound that actually smells completely different. All right, and there are a number of differences that are pretty important. There was one particular case of a pharmaceutical back in the olden days, all right? It's back before we really appreciated what chirality was, because chirality is such a small difference. You can't really even separate them, so how do you know? So if you make a compound that kind of looks like this, all right? And so this happened in 1957. In 1957, as a hallmark year for learning just how important chirality is, because this molecule entered the market. All right, and this molecule is called Solidimide, and it is this molecule in particular, is pretty good at getting you to go to sleep. And it helps with morning sickness. So this is a good morning sickness. This is a good morning sickness drug. And in this particular stereo center is the R-thalidomide compound. But back in the 1957s, the real importance, they knew about stereoisomerism. They didn't know necessarily the importance of this. And so when you make the original prep for thalidomide, didn't bother to separate, or it was not specific in making just the R. It also made the S compound, okay? Or you can make the S. It's certainly a lot easier and cheaper if you use it, if you do the S synthesis, right? And so what that then gives you is a racemate, and, you know, under normal circumstances, who really cares, right? The problem, though, is that S-thalidomide is what's called tetratogenic. All right, tetratogenic means monster forming. And so if you give it to healthy people, nothing happens. But if you give it to a pregnant person, it causes mutations in the fetus. And one of the big mutations that it caused was just cease the development of limbs. And so in the process of prescribing these across 46 countries, 10,000 babies were born with abnormalities. Either they had a very tiny arm with an underdeveloped hand, or tiny arms, tiny legs. Nobody knew exactly what was going on. But this is an example of a tragic consequence of not understanding your chirality. And of course that comes from, like I said, that proteins themselves are chiral. All the amino acids, with the exception of glycine, is chiral. And when they are put together into these chiral peptides and chiral proteins, and that is what builds our sensors, that is what builds the components that recognize drugs, which means that your proteins have the ability to recognize an R and an S molecule differently, okay? Because chiral compounds can interact with each other differently, all right? And so as a consequence, we now understand and are much more cautious about giving people medication as mixtures of drugs.